Hey everyone, and welcome to this video concerning the use of Cramer's rule to solve a system of linear equations. And in this video, as you can see over here, we're going to solve this system of two equations in two variables, but with the intent of, in future videos or further videos, of generalizing this more for systems of order n, in which we would say there would be n equations and n variables. But Cramer's rule is actually named after a mathematician, Gabriel Cramer, excuse me. But it's a really nifty rule for solving systems of higher order, especially when you have solutions that are rational. And you're going to see here that all the solutions are actually considered rational. But when you're talking about things that come out to be really wacky fractions, it's just not very desirable to do it in the old-fashioned way of linear combinations. So anyways, we're going to start by kind of generalizing this rule over here on the right. But we're going to start by talking about a system of equations, and here's what we'll do. We'll say that we've got a11x plus a12y, and we're going to call this equal to c1. And how about we call this one a21 sub 21x plus a sub 22y is equal to c2. And sorry to be very, very roundabout about this, but anyways, you can kind of see that I've kind of played with the coefficients in such a way that we're probably, and you guessed it, going to create what we're going to call the coefficient matrix of this system of equations, which essentially just really concerns itself with the coefficients of these two equations. So we're going to call this coefficient matrix A, and it has order 2 by 2, 2 rows, 2 columns. But matrix A, we're gonna call this matrix with entries A11, A12, just denoting that it's in the first row, first column, first row, second column. But of course, we got here A21 and A22. But we are going to refer to this as the coefficient matrix of this system, okay? And you notice that this is a square matrix. And so the thing here is, when we talk about Gabriel Cramer's rule, or Cramer's rule, we're talking about systems that have just as many equations as they do variables, which produce coefficient matrices that are square matrices. And in its essence, we're going to be dealing with determinants, which are only defined for square matrices. Another matrix we're going to create here involves these two constants off to the right, okay? But no shocker here. We are going to refer to this as the constant matrix. And I guess I could refer to this as C, but in this instance, it's a 2 by 1 matrix, a 2 by 1 matrix. But this would be the matrix consisting of the constants of the system, so C1 and C2, just for the sake of simplicity. Anyways, this being said, the neat thing about Cramer's rule is, and this is, I know, specific for a 2 by 2, but it essentially says if you wanted to find the solutions of the system, which would consist of some ordered pair xy, if it exists, we'll talk about instances where it wouldn't exist, then it must be consistent with this form. So here's what we're going to say. We'll say the solutions of the system are defined in general thusly. We say the x value, or the x solution of the system, is over the determinant of A, this value. It'd be necessarily the determinant of, we'll put C1 and C2 here, and then we're going to put A12 here, and A22 here. But the determinant of this matrix, and here's what I really want you to see. When we're solving for the x value, or the x coordinate of our solution, or ordered pair in this instance, you'll notice that I took the two constants over here, these two constants, and I inserted them into what we would necessarily characterize as the coefficients, where the coefficients of x used to be. So since we're solving for x, we kind of plug in the constants over here for the column where the x coefficients used to be. Now, to be more general about this, again, we're going to divide this by the determinant of the original matrix A, but in order to find the y part of our solution, it'd be this. We have A12 and A21. Pardon me, this is A11. Don't know what I'm thinking here, but A11 and A21, where we've kind of left the x coefficients alone, but since we're solving for y over here, we're going to insert the constants into the y column. If I had to kind of put this in my own words, and I know this isn't very, very math speak here, but basically what I'm saying here is for a system of order n in which there are n equations and n variables, the x part or the y part or the z part or the w part, or in general, whatever part you're solving for here, it's always of the form where it's a rational number over the determinant of the original matrix, but on top you have the determinant of a matrix in which we've inserted the constant terms in for the specific variables column we were solving for. So here we were solving for x, we insert the constants into the x column and find this determinant. And here we're solving for y, we'll insert the constants into the y column. And this would proceed so on and so forth. If we were solving for a z, we would have a 3 by 3 matrix, but we would insert these constants here into the z column, or the coefficients, where the coefficients of z's used to be given the original system. So let's kind of take a look at this one over here. And I know, I'm doing this in my own little world and language over here, but maybe if you see it run once or twice, we'll get the hang of it. So you're going to notice we have a system of, we're going to call it order 2 here, but necessarily we have 2 equations and 2 variables. So let's go ahead and start by making our coefficient matrix, and we'll refer to this as matrix A. And this is a 2 by 2, okay? This 2 by 2 here, by definition, is it's the coefficients of the system. So we've got here 4, -2, 3, and -5, okay? So now this being given, we're going to come up with our constant matrix C, and our constant matrix C here is just the matrix consisting of one column, but with our constants that we had in the original system. Now, this being said, what we want to do first, and you know what, we don't have to do this first, but I find it's very beneficial. We're going to go ahead and find the determinant of matrix A. And if you haven't already kind of thought about this over here, but all of our solutions were divided by this determinant of A. And it's really going to cause an issue if we have a matrix that happens to be singular. That is a matrix with determinant 0, because what's going to happen is now we have necessarily values here that are undefined. Of course, that would necessarily, if this matrix is singular, it would represent a system that we would say is necessarily inconsistent, or a system that would have no solutions, which in a two-dimensional sense would be, say, 2 lines that are parallel. And you might go back and try this sometime, creating your own system in which you create a first equation, but then say scalar multiply that equation by, I don't know, 2 or some scalar, and come up with a second equation. But they would necessarily be the same equation, really, and you would see that you'd come up with a determinant of 0. And there'd be no solution in an inconsistent system. But let's go ahead and find the determinant of A. So the determinant of A, remember, we defined this with the 2 by 2 in a 2 by 2 sense, is the product of the main diagonal minus the product of the opposing diagonal. So sorry to kind of carry my work here down to here, but I'm going to drop this down here. When we say the product of the main diagonal here, we end up with 4 times -5, which is determinant of A, is equal to then -20. Of course, by definition, this is minus, it's a difference, minus the product of the opposing diagonal, which in this instance happens to be -6. So we do end up with here, you see this, plus a positive, of course, but we end up with a difference of -14. So we have a negative determinant, which presents no real issues here, but we say -14. Okay, we need this number because it will be the denominators of our individual values in which we're solving for, which in this case we're solving for x's and for y's. Okay, that being said, let's go ahead and set up our solution in general here, but we say it's a 2 by 2 system, so we're solving for x's and y's, but here's what we know already. The solutions, their denominators are going to be -14, and it may happen when we end up finishing this problem that those actually simplify down. But we say, okay, since we're solving for x in this little portion of it, it's going to be the determinant of the original matrix in which we took the constants and we insert them in for like the x coefficients where they used to be. So in this instance, since we're solving for x, we're going to drop those in there. We say 10 and 11. And then we just kind of leave everything else the same. We say -2 and -5 here. Okay. Since we're solving for y for this part of our solution, it's still the determinant of the original matrix, but in this instance we're going to insert the constants for where the y coefficients used to be. Okay, and we're going to leave the original x coefficients alone. I can tell you right now, if you're a student and you're watching this video and you're looking at this, if you put this on your test paper, there's no way that your professor or teacher can tell you, look, you're wrong. This is actually the solution right here. All it requires now is a little bit of simplification. So we're going to go ahead and finish this up by going ahead and carrying out the determinant of these matrices, but we say 10 times -5, of course, is -50. So -50 minus, and in this instance we're taking away a -22. So we're really adding this. So we say plus a +22, and that presents us with the difference of -28, which you're noticing probably already is going to react very well with this. But we say, okay, so -28 over -14. And let's go ahead and work this other determinant here. We've got 4 times 11, so of course that's 44, and 44 minus 3 times 10, which is 30, but presents us with a difference of 14. So we say 14, and of course this was over the determinant of the original matrix, which was negative 14. So of course we're going to go ahead and go through and simplify this, but this would imply that our solution using this rule, oh pardon me, is equal to positive 2 comma negative 1. And all that's left to do really is go back with the system and plug this back in and solve and check that this works out. Real quick note here, I just want you to know this, because if you're looking at this like I am, or if I would be if I were a student, I look at this and say, why couldn't we just run linear combinations on this system? It would have been very easy to eliminate and then back substitute. And you're absolutely right. Of course, it's just choosing the right tool for the right job. But again, Cramer's rule, I mean, imagine these wouldn't simplify very well. It'd be nice if you were getting rational solutions, because I know that everybody just loves fractions, and sadly I actually do. But anyways, if you had, I'm going to say highly rational answers, even though math people will cringe at me saying that. They're all rational. But really funky rational numbers, let's put it that way. And also, matrices or systems of higher order, Cramer's rule really works. So on to the next video.